we started it already last time. It's a pretty simple method if it's for one-by-one transformation. So if you have a y, which is a function of a random variable x, and we here in this chapter we always assume that x is have a continuous density. So x is continuous with density f of x. So has density x has density f x of x. Right? So so in this case we are interested to figure out what's the density of y. So it's pretty simple. So we just kind of write that f of y of y, right? So and so here we have something like a picture. So here's some range of x, right? So this is something like a range of x, which means that outside of this range the random variable is 0, density is 0. So here is some x and it's mapped to some y. So this is a transformation g. So y is equal to g of x. Right? And so now, so and the range is kind of, it's mapped, range of x is mapped to range of y. And so now in this case, if we have a y, which is a function g of x, then we can also kind of define the inverse function g of 1. And so we can write that x is equal to g minus 1. So this is inverse function of y. So and f of y will be equal, okay, so it will be equal to the density of x evaluated at this point x, the corresponding point, which is kind of written at g of minus y of y. Right? But so we also need to correct it because because this range stretches. Right? So and we saw, I think we saw in the last lecture, in the end of last lecture, so that the right correction function is just the derivative of this inverse function. So it's d over dy g minus 1 of y. And well, kind of turns out that we'll need to take absolute value of this function. So because this derivative, the size of this derivative, it measures the amount of a stretch, but also kind of up to the sign. Right? So we'll need that it was a positive measure of the stretch. And then here we assume that this g is a one-to-one function. So it's a one-to-one function. And so this is needed because we only want to have this inverse function, g minus y of y. If there are 2 points which go to 1y, then it's not clear how to define this inverse function g minus 1. Okay, so now, well, this is it kind of. It's very easy formula kind of. So this is essential formula that we have, very easy to use in practice. So let us just recover the 2 examples that we had last time and which we did using cumulative distribution functions. So example, first example, and it was that we have a x, right? X has density, right? So it was f of x equal to 2x if 0 smaller than x smaller than 1 and 0 otherwise. Now so this new random variable y, Right? So sometimes kind of in the lecture notes, I sometimes call it U, sometimes Y. So let's call it here as Y. It's equal, here is 3x minus 1. 3x minus 1. So what's the density of y? So Fy of y. And this is kind of just a kind of, this is kind of a direct application of this method. So we write that x, so we write inverse function. So x is equal to y minus 1 divided by 3. Right? So so our, in this case, our g of x is equal to 3x minus 1, and the g minus 1 of y, in this case, it's equal to y, sorry, here's plus 1, right? So plus 1, y plus 1 divided by 3. So this is, and so we just write down the density. So, so this g of y of, so here should be, sorry, f of y, it's equal to, right, so take the f, so this is 2x, but instead of x we write the corresponding expression in terms of y. So f of 2 of y plus 1 divided by 3. And the only thing that we'll need also to multiply it by the derivative of this function. So multiply by the derivative of function y plus 1 divided by 3, this derivative is 1/3. So this is d over dy of y plus 1 divided by 3. And also kind of in principle you need to write absolute value, but his 1/3 is a kind of, it's already 1/3, right? So it's already positive. So eventually we'll get that this is equal, so Fy of y is equal to, right? So 2y plus 1 divided by 9. Right? And the only thing remains, it's kind of, well, this is only true on the range of y, right? So what's the range of y? Well, in this case, kind of a range of x is equal to 0 and 1, right? So it was 0 and 1. This is range of x. And kind of, so this is a linear transformation. So it's one-to-one linear transformation. So we see that 0, okay, using this formula, that 0 goes to 3 times 0 minus 1. So it goes to minus 1. And oops, to minus 1. And 1, it goes to 3. It goes to 3 times 3 times 1 minus 1, so it goes to 2. So the range of y, so this is range of y. So we know that this is valid only if y is greater than minus 1 and smaller than 2. And 0 otherwise. And so this is kind of very simple, kind of without any kind of, so it's much simpler when we're using the cumulative distribution functions. Right, so now kind of, okay, so this is the first example. So example 2, it was example with a little bit more complicated function and a little bit more complicated density. So here's a f of x of x. So example 2, f of x is equal to so 6x 1 minus x, where x, this is a beta distributed random variable, so x belongs to 0 to 1, so and 0 otherwise. So we write that, okay, so y is equal to x to cube. And again, so we can easily see that x cube is 1-to-1 on the, it's 1-to-1 function. Right? So it's easy to invert. It's write x is equal to y to the power of 1/3. Right? And so we write that f of y is equal, okay, so we just take this 6, and instead of x, we use this expression, but with the small letters, because we're talking about values. 6y to the power of 1/3 multiplied by 1 minus y to the power of 1/3. And again, so the last thing is just we need to write down what's the derivative, right? So there will be derivative d over dy of a function. Here will inverse function, so this function, so y divided to the power of 1/3. Y to the power, so it's equal to, so if we take this derivative is equal to 1/3 y to the power of minus 2/3, right? Y to the power of minus 2/3. And so when we multiply, so here's 1, y to the power of 1/3, so y to the power of minus 2/3, so altogether will be, okay, so 6 divided by 3, so 2y to the power of minus 1/3. So because we multiply y to the power of 1/3, here's y to the power of minus 2/3 here, and here's y to the minus 1/3. So, okay, so and again, so you need also to write down what's the range of this thing. So, and this is if y is greater than 0 and smaller than 1, just because kind of if you look at the 0, 1, this is range of x, and you see what happens when you map by x cube, right, by this function. So this is 0 is mapped to 0 and 1 is mapped to 1. So the range doesn't change in this example. Right? So this is a x cube. So this is a range of y. So okay, so 0 otherwise. So kind of very simple. So maybe kind of one more example, right, of using this. So this is kind of 4 one-to-one transformation which have an inverse. Right? So which are one-to-one. This is the simplest possible method. So example 3 would be example 3. So say you have a x is a standard exponential. Random variable, and we are looking at y is equal to square root of x. And so now what's the density of x? Again, so well, what it means that it's standard exponential random variable, it means that f of x is equal to e minus x if x is greater or equal than 0 and 0 otherwise. And so now kind of we write down, so y is equal to square of x means that x is equal to y squared. And then after that we just write that f of y is equal to e minus, so plug it in this x, so minus y squared, but don't, so just not forget to write down that you also need a derivative, d over dy of y squared. So altogether that you'll get that this is equal to 2y e minus y squared, and here's if, right? So and after that you see how this range of x maps. So range of x is it's all numbers greater than 0. So if you take a square of them, it will still be mapped to all numbers greater than 0. So this is range of y is the same. So it's from 0 to infinity. Range of y. And so if y is greater than 0 and 0 otherwise. And so this is it. So now the question is, what happens if it's not? So there are many examples of this type. So so now what happens if the transformation is not one-to-one? So this is we deal with just the simplest case when the transformation is one-to-one. What if it's not one-to-one? Well, in this case, what you have a picture like that. So you have some y here, right, in the range, and you have a two or more. So let's say two points which are mapped to the same y. So consider the case when it's not one point which is mapped to y, but two. So what if G is not one-to-one? So in this case, well, intuitively, so it's easy to explain what happens intuitively in this case, right? In this case, you just have a you are looking at, again, so repeating this intuition which we have before, you're looking at the interval from y to y plus dy, right? And you want to figure out what's the probability that the random variable y lands in this interval. Right? So you have this interval here. You're interested in this interval. And so now, well, if you take the the inverse, if you take the inverse transformation with this interval, it turns out that it's in the after the inverse transformation there will be two intervals. Right? So there will be interval which is from x1 till some point here. Right? So some x1 plus something like a dx, a dx depends on the dy. So, and there will be a small interval here. Right? So there will be two intervals here, which will be both mapped in this interval over next to y. And so the probability that the random variable 1 belongs to the interval from y to y plus dy will be equal to the probability that random variable x is in interval next to x1 plus the probability that the random variable is next to x2. Right? So to get the total probability, you need to sum these two things together. So this gives you a formula for this particular case. Right? So you just need to sum over all possible inverse images. So suppose that every y has two pre-images, x1 and x2. So that means that we have a g of x1 equal to y and g of x2 equal to y. Okay, so now in this case, so we can define we can define two functions. Can find g of -1, so g1 -1 and g2 -1. So in this case, we have a two inverse function. Maybe not everywhere. Maybe sometimes at some points it will be 1, but kind of at most kind of points it will be 2 preimages, and we are interested in most points in this case in probability theory. And so such that g1 of -1 of y is equal to x1, and g1 of g2 minus 1 of y is equal to x2. So, and well, kind of in this case, the formula will be just kind of like previous, but a sum over x1 and x2. So in this case, you will have f of y will be equal to f of x evaluated at this x1, which we can write as g1 minus 1 of y, and we'll need to multiply by the stretching factor. So d over dy of g1 minus 1 of y absolute value of this thing plus the second term. So f of x of g2 minus 1 of y multiplied by the absolute value of this stretching factor. So d over dy g2 minus 1 of y. Well, this formula seems to be kind of more complicated. Right? And well, this is a more complicated situation. Better if it doesn't happen, but if it happens, it can be applied. So here's a very simple example when it can be done. Right? So example, so if you have a x is uniformly distributed, x uniformly distributed on the interval form -1 to 1. On -1 and 1. Right? And so y is equal to, say, x squared. So you know that kind of in this case, there is no one-to-one correspondence, right? So if you have a function with this function g kind of, so it looks, this is a function y is equal to x squared. Right? So this is x, this is y. And if you fix some specific value of y, well, it will have two preimages. One will be so minus. So if you take inverse, the next one will be square root of y, right? And next two will be minus square root of y. Right? So we will be kind of, for a specific value of y, you have a minus square root of y and square root of y. So this is the situation exactly like in the previous, in the formulation. So you have a function g, and in its inverse, it's actually not one function but two functions, right? So now, if you ask, we can ask the question. So what's the density function of y? And in this case, maybe kind of it's easy to figure out, right? So it's kind of, in this case, you write that f of y is equal to, now what's f of x of x? So f of x is equal, since it's uniformly distributed between -1 and 1, so the density is equal to 1 divided by the length of the interval. So it's 1 divided by 2 if x belongs to the interval from -1 to 1. And it's equal to 0 otherwise. Right? So, okay, so the density in this case, what you'll need to write is, okay, so using our previous formula, so it's equal to 1/2. So this is the first part. And happily for us, this density doesn't depend on anything, so it's constant. So it just will be 1/2, right? So, right, multiply, and after that, we'll need to write here d over dy, and here we'll take x1, so square root of y, right, an absolute value, so maybe square root of y small. absolute value of it. And after that, the second part, so here will be again 1/2 just because the density of x doesn't depend on y. So it still will be 1/2 here, right? Multiply, and here the absolute value of d over dy, and here minus square root of y. So this is the thing here. Right? And well, kind of in this case, kind of it turns out that both this derivative, so this is equal to 1/2 multiplied by 1 divided by 2 square root of y, right? And here's plus 1/2, in principle minus 1 divided by 2 square root of y. But it's also here an absolute value, so it will be 1 divided by square root 1 divided by 2 square root of y. So altogether you'll get that this is equal, okay? So 1/2 here, so 1/4. Here's also 1/4. So summing together, we'll get this is equal to 1/2, 1 divided by square root of y. Right? And the only thing that also you need to write the range, kind of, so range of, how the range of, what's the range of y? And so before that, it was right. Connection is not stable. Okay, so the range, right? So this is a range of x, right? And it's mapped, so it's mapped by function x squared. So it's mapped to, so -1 goes to 0. Sorry, -1 goes to 1, and 1 goes to r. So it's mapped to from interval from 0 to 1, right? So kind of -1 to 1. This interval here, if you take a square root, then it goes to the interval from 0 to 1. So the answer will be 1/2 1 divided by square root of n if y is in this interval 0 to 1 and 0 otherwise. And so this is a super simple example, super simplified example that shows how well, kind of in principle, it's possible to apply this method even if the function is not one-to-one. It's just kind of you'll need to use this method. Maybe kind of maybe kind of on some places it will be 2 pre-images. In some places it will be 3 pre-images. Maybe you'll need to split it up in complicated cases, but kind of, well, we will not look at the complicated cases. Okay, so this is the how this method works for one-to-one function. It's extremely simple, so extremely useful in this case. So the most simple and useful method if it's function of one random variable, PDF transformation method. Now, so what happens if we have a function of several random variables? In the previous lecture about the cumulative distribution function, we saw that it is possible to deal with this, but it becomes a little bit more complicated. So kind of I lost my way in the formulas, right? So it's slightly more complicated. What about the density transformation method? Well, so one thing is, well, it's even difficult to apply immediately. Right? So it turns out that it doesn't kind of it's very useful, but it's not much simpler, kind of. So right, so here's this PDF transformation method for functions of several variables. So now here's a motivating example. So this is what we did in the last class. So this example was that we had a x and y have joint density. So this was f of x, y, and it was equal to 3x if 0 smaller than y, smaller than x, smaller than 1, and 0 otherwise. Right? And we looked at kind of, let us call this variable u as it be before, so it's equal to x minus y. Right? So and the question was what was the density of this difference, fu of this u. Right? So this is from our previous lecture example, right? And okay, so now so this was the picture. Right? So this was our picture. Say okay. So this was our range. So this is y, this is x. So this is y, okay. This was y equal to x line. So this is 1, 1. Okay, so now, so if kind of we want to apply the method of PDF transformation method, so we want to say kind of that this, so we would say that this is equal to f of x, y, right, of x, y. So kind of, and look at what's the, what's the x and y which corresponds to u, right? So this would kind of suggest to do it. But if you look at what the x and y which corresponds to some specific u, right, we see that kind of if we fix u, right, if we fix u, then there are many points which corresponds to this u. So kind of all these points are like here. So this is if y is equal to x minus u, right? So then the difference, when from this you see that x minus y is equal to u. Right? So on all these points of this line, the u takes the same value. Right? So now our method doesn't work because kind of it's kind of you cannot pinpoint a specific point at which to take the density. Our method was line of right. So kind of if you want to calculate the density at specific point, you'll need to look at what's the corresponding density for x and y, right? For the variable from which you take the take the function, and kind of, well, maybe kind of multiply by some stretching factor, and this will give you. But in this case, there are kind of infinite number of the pre-images, right? In our previous example, there was a 2 pre-images. So kind of our function x squared mapped kind of negative values and positive values to the same value, but there was a 2 pre-images. So we can add the density for these pre-images. Here there are infinite number of the pre-images, so we don't know how to do it. Okay? So we don't know what's the x and y which correspond to this specific u. There are too many of them. So we'll need to integrate somehow sum these densities together, but it's not clear how to do it. And so the way out here turns out, and the way out here is to introduce some additional variable, right? So something like kind of introduce something like a variable v, which may be equal to some of these things. So maybe it's equal to x, or maybe it's equal to x2. So it's equal maybe kind of so to y, right? right? And kind of write what's the joint density of FUV. So this is new thing. So write the joint density of FUV of UV. Because in this case, you will be able to write down that this is equal to F of XY, XY, XY multiplied by some factor. Because for specific value of U and V, right, so you can pinpoint. So this is kind of, this is the point which corresponds to specified value of U and to specified value of V, which is equal to Y, right? So kind of, so this is in our case, so this will be this point. So if it say that if you kind of specify Y, and after that you figure out what's the joint density of U and V, you just integrate out of V. So after that you write that F of U of U just equal to the integral of FU V of UV of dV. Right? So over something. So kind of right. So kind of it's basically kind of doing the trick that we did in the previous example when we sum the density over the preimages. So we also integrate the density over the preimages here. Right? So okay. So now so this would be our plan. But before we're doing that, we'll need to see how kind of calculate this thing. So because I wrote here 3 dots and it's not clear what it means. And so this was a motivating example. So the plan would be in this example would be introduce another function of X and Y, so which will be called maybe G2 of XY, V is equal to G2 of XY, such that map U equal to G of X, Y, V equal to G2 XY is invertible, is 1 to 1 map. So, and then second thing, so this would be first one. Second thing, so apply formula star. But we don't know yet the formula star. This is kind of, we'll need to kind of to specify exactly what this formula star, because there are some unknown thing here. So let us kind of first of all write down what's this formula star in more detail. So kind of so formula star in detail. So here what we'll have, okay, so let us repeat kind of what we'll have. So we have U is equal, so we have U is equal, okay, we have a transformation so G at which G which maps X and Y to U and V. So this is something like we have a x, y, and this kind of transformation. So it takes the points x and y and maps it to some other pairs of point u and v. So in coordinates, it will be something like u is equal to g. Well, kind of here I wrote g, simply g, but kind of let us write here g of 1 of x, y. And v will be kind of another function g2 of x, y. So it is assumed 1-to-1 transformation. And so which means kind of that if you have a u and v, you can recover x and y. So this is there is an inverse transformation. Right? So there is an inverse transformation. And well, we call the adverse transformation g to the power of -1 before. Let us kind of call it h here. So well, this is equal to g -1. And so and it maps u and v. So it maps things back. From u and v, you go to x and y such that which is inverse. If you do g and after that h, it will get back to the x and y. And so basically, you solve this system equation of in terms of x and y. Right? So this is an inverse transformation. Right? So this is how you obtain it. And it will be looks like that. It will be x is equal to h1 of uv, and y will be equal to h2 of uv. So it just kind of you take this system, right? So this system and calculate it, solve it in terms of x and y. So this will be the second system. Kind of this will be in your inverse transformation. And so now our equation here will be what is the density? What is the density of u equal to g1 of x, y? So this is just this was just a description of a transformation. Right? So here's we'll say that we'll take the random variable x and y and apply this transformation to these random variables, right? And so here's u is equal to g1 of xy and v is equal to g2 of xy. Right? So what's the density of these two things? So the joint density of u and v, if the density, again, joint density of x and y is f of x, y, x, y. So this is our equation, and here's the answer to this question, which we will not prove, right? So in the previous case, I proved that with the formula. Here I just I do it by analogy, right? So I'm writing that actually the joint density of u and v at u and v, and then saying, okay, it should be equal to f of x, y at the point which corresponds to the point u and v. So what's this point? Well, this point is h1. So I'm looking at this kind of formula. Say so instead of x, I take h1 of uv, right? And instead of y, I take h2 of uv. So this kind of it was at xy, but I'm interested kind of only in the points. So I fixed u and v, and kind of I want to apply the density at x and y, which corresponds to it with uv. Okay? So now, and we know kind of from our previous case about the univariate random variables, when just one random variable, we need to multiply by the stretching factor here. So, and again, so I said, well, kind of, unfortunately, I'm not going to prove it. I just kind of tell you that it's something like that we already seen in the multivariate calculus. And so if you kind of want to figure out how the area of the area changes, area element changes when you apply some transformation, then you calculate something which is called Jacobian. And so when you calculated how they change the variable in integral, then you calculated Jacobian. Right? So, and this was a kind of measure of how the area element changes if you go to a different set of the variables. And we're doing exactly the same thing here. And so this is the change of the area element, change of how this transformation stretches the thing. So I need to here to write down this transformation. I write this absolute value. It's same thing like before. It should be absolute value, but here previously it was derivative. Right? So instead of derivative, I write here Jacobian of the transformation and the transformation h. So the notation, well, kind of, there are many notation for the Jacobian. I use kind of, so here d of h of uv over d of uv. But it's kind of, it's just a notation. You could also write some other notation here. So what's important here is what's the definition of this thing. So this dh of uv over duv, it in principle even kind of, so typically the Jacobian is just kind of this thing already is absolute value. And so this thing is a Jacobian of transformation, Jacobian of h, of this transformation h. Right? And so by definition, it's absolute value of a determinant of this matrix. So this will be d of h1 uv over du. Here will be d h1 of uv over dv. Right? Here's dh2 of uv over du, and here's dh2 of uv over dv. And so h1, you take h1 it's in rows. Right? So the first row is that's h1, the second row is h2. And the first column is taking the derivative with respect to u, second column taking the derivative with respect to v. And if you forgot what is the determinant, right, so kind of you're supposed to know it, but kind of if you forgot, kind of it's equal to the kind of cross product. You kind of multiply, sorry, not cross product, it's equal to the product of the diagonal terms minus the product of the anti-diagonal terms. So it will be equal to dh1 of uv over du multiplied by dh2 of uv over dv. So the product of the diagonal terms minus the product of diagonal terms, dh1 uv derivative with respect to dv multiplied by dh2 uv over du. So this is kind of formidable, but it's kind of, you need to know how to calculate it, to calculate the integrals, change of the variable integrals in the calculus and multivariate calculus. So I assume that you at least seen this before. Right? And so, okay, so this is the formula actually. This is already kind of, this is our formula which we talked about before. So if you have a transformation from x and y to u and v, right, and this is one by one. So here's how you can calculate the density of u of v if you know the density of x and y. Right? All right, so maybe kind of a small break here, and after that we'll continue with the example that we had before and figure out how to do it, kind of using this formula. All right. So let's kind of restart. So, and so guys, we are going to finish this example. So here's another example. So we have a f of xy is equal to 3x if 0 smaller than 1, smaller than x, smaller than 1. Right? And 0 otherwise. And so in this example, it's always useful to have a picture. So, well, maybe I'll put it from here. Well, we maybe kind of redraw it. Right? So we have a picture like that here. So here's so it's 1, this is y, this is x. So this is our range. And the u, the random variable which we are interested in is u. It's u equal to x minus y. So it's excess of x over y. So in our interpretation was that x is the beginning amount of some material. So for example, gasoline in there, it's in the beginning of the day, y is the amount of gasoline used, and u is kind of the remainder, kind of at the end of the day. And so we are interested to figure out what's the this density of u if we know the joint density of x and y. And so now, in kind of the trick that was suggested is to add additional variable, which is kind of just well, so that we could use this PDF method. And so just additional variables, so that this transformation is 1-to-1, and kind of we can use y, for example. Could use x, kind of, well, but let's use y. And in this case, well, kind of first thing to do is, well, what's the inverse? Kind of where we choose this. This is have an inverse transformation, and all right, so we already know that y is equal to v. Right? So this is from the second equation, and then from the first equation, when this x is equal to, right, so it's u plus y. So it's equal u plus y from the first equation, but we already know that y is equal to v. So it's equal to u plus v. So this is our inverse transformation. This is something which we'll call G transformation. This was we'll call that this is H is equal to G minus 1. So this is the inverse transformation for the first one. And the nice thing that, well, it exists, kind of, it's 1-to-1 transformation. And so now what's the, well, kind of in our formula, we also have a Jacobian of this inverse transformation. So what is it? So Jacobian of H. And so, okay, so this would be equal to absolute value of the determinant. And here you'll need to write down the partial derivatives, right? So kind of what's with derivatives? So it's derivative over u, partial derivative over u of the, okay, so the first h. The first h is u plus v. So derivative over u of u plus v. And the second column is derivative over v of this u plus v. So u plus v is just kind of the first inverse function. Here we have d over u of the second inverse function, which is v. And the second element in, so the last element in this matrix will be d over dv of v. All right, so what is it? Excuse me. Okay, so it's equal to determinant, absolute value of a determinant. So, and we take this derivative, so we'll get here the first partial derivative here is, okay, is equal to 1. Derivative of u by u is 1. Derivative of v by u is 0, so it's 1 here. So what we'll have here is 1. Okay, so the second element 1. Here's derivative over u from v, which is 0, right? And here's derivative from v over v, so it's 1. And so it's equal to absolute value of 1 times 1 minus 1 times 0, so it's equal to 1. And so, so happily here the determinant is just equal to just 1. Right? So with Jacobian, in this specific case, it happens to be that we shouldn't worry about it. And so this is not very usual, kind of maybe not very instructive, but it happened to be that with this transformation, kind of Jacobian is equal to 1. Right? And since this is, so after that, we just write the joint density, right? So f of u v of uv is equal to, so f, right? So which is equal, so here should be f of x, which was equal to 3x. But instead of x, we'll need to plug in its expression in terms of u and v. So 3u plus v, so this is x, right? Our former x. Right? So multiplied by the Jacobian, which is equal to 1 here. Right? So it's equal to 3u plus v. This is great. So this is was very easy to compute, except that we don't really want this thing. What we want is the marginal density. We want the density of u, not of the density of u and v together. And so we will need to write that this is integral from this is integral of so f of u is equal to integral of this f u v of uv over dv. So we're integrating out this. So it's equal to the integral from 3u plus v over dv. The only thing that it's kind of integral over what region? Right? So what's the bounds of this integration? And then to figure out what's the bounds, we'll need to know not only this thing, we will need not to know if the density is equal to 3 plus u plus v, but we also need to know where it's equal to 3u plus v. And what's the range of u and v? So the question is, what is, so the question is here, right? And the question is, what is the range of u and v, right? And in principle, the answer is easy. So range of u and v is just equal to g, kind of this transformation g applied to the range of x and y. So kind of if you look at this, well, this is this yellow thing which I for some reason draw but have not used. So it's equal to range of x and y. Okay, so it's just kind of right. So the transformation g takes this range and maps to something, and I will just kind of this thing will be range of u and v to which it maps, but to what? Right? So let us kind of take this. Maybe I'll try to do it. I'm not sure if I'll be able. And so, so it should be, so this is should be mapped by g, this transformation g, right? And remember that the g was given just by the formulas that u is equal, so the g is given by the formula u is equal to x minus y, and v is equal to y. Okay, so it's mapped to some region here where this is u and v. So in the question is, well, kind of what's the image of this triangle under this transformation? So this is our triangle, which we are interested how it's mapped, and this is our transformation. Well, in this specific case, it's very easy. Kind of the difficulties are kind of in the difficulty happens in our examples. So then this is not so easy to figure out. Here, the transformation is linear. So this transformation is linear. And it means that it takes lines and puts it into the lines. Right? So, and if you want to figure out what's the kind of the image of this thing, you just need to figure out what's the images of the vertices of this triangle. Right? So what's the images of the vertices? Right? And connect it with the lines, because the lines will go to the lines under this transformation. Right? So you'll figure out, okay, so there are three kind of vertices here, 0, 0, then here's 1, 0, and here's 1 and 1. And so you want to figure out what's the images of them. So you'll see G of 0, 0. Right? So what is it? Right? So U kind of, in this case, so U is equal to X minus Y. So the first coordinate here will be 0 minus 0. Right? So 0 minus 0, and the second coordinate is just y, so it's y, so it's 0. Okay? So it's equal to 0. So the first point goes to itself. Right? The second point, so g of 1, 0. Right? G of 1, 0. So maybe I don't need actually to write this second bracket here. So g of 1, 0. Well, maybe you can, because it's g of 1, 0, this point 1, 0, maybe I'll need to write it. It's equal to, okay, so x minus 1, so 1 minus 0, and the second 0. So it goes to 1, 0, to itself. And nothing interesting, kind of, right? So here 0, 0, 0. What about g of 1, 1? Right? So it's equal to 1 minus 1 and 1. So it goes, well, something different than before, 0 and 1. So now these points are, okay, 0, 0. Then another one is here, it's 1, 0. And the last one, the image of 1, 1, it's here, it's 0, 1. So this is 0, 1 point. So it turns out that this triangle goes to this triangle. So this is images, so this is the range of UV. So okay, so this is our range UV. Yeah, so in principle, the answer to the question what's the joint density of the U and V would be kind of, it's a bit different from before. So it's, yeah, the joint density is equal to 3U plus V, but only if we in this range. Right? Now, okay, so f of U V of UV is equal to 3U plus V if U V belong to the range. So, and we can describe it by inequalities, but kind of geometrically it's because it's in this triangle, right? 0 otherwise. And so now at this moment we can answer why we did this, because we want to figure out what's this f of u, right? And we wanted to figure out, we will need to do an integral of f of uv over dv. We want to figure out what's this marginal. So we'll need to figure out what's if you fix u, right? So what's the change in the v, right? So, and it turns out, well, if you look at this thing, so, well, you still need to know what's this thing, but this is clearly that this is v is equal to 1 minus u, right? This is line. So you see that, well, if you fix u, then v can change only from 0 to 1 minus u. So you figure out kind of when you calculate the marginal thing, you figure out what should be the limit here. So here will be 0, should be 0, and here should be 1 minus u. So if you fixed u, then if you fixed v, you to calculate the marginal distribution, you'll need to integrate over this interval, right? So the interval have a v which is changing from 0 until this thing. So this thing is equal to 1 minus u. And so so you write that f of u in numbers, it's equal to the integral from 0 to 1 minus u. He will have 3u plus v dv. And after that, well, now finally, well, kind of, it would be easy if I wouldn't explain things, right? So just wrote the formula, right? So this is equal, okay, so you take antiderivative, here will be 3uv plus 3 half v squared, right? So evaluated from 0 to 1 minus u. Right? So evaluated with from v equal to 0 to v equal to 1 minus u. Right? So it's equal, okay, so we plug in, instead of v, plug in 1 minus u, we'll get here as 3u 1 minus u plus 3 half 1 minus u squared. Right? And minus, well, minus something, but it's kind of evaluate this thing at 0, it gives you 0, right? So minus 0. Right? So what is it? So it's equal to 3u minus 3u squared plus what we'll have here. Well, still not doesn't look right. Maybe right. Okay, so let us look. So 3 half, and here's 1 minus 2u plus u squared. So it's equal to, okay, so 3 half here. So here's 3u minus, here's also 3u. So this linear term cancel out, and here's minus 3u squared, and here's plus 3 half u squared. So minus 3 half u squared. So equal to 3 half of 1 minus u squared. So let's see kind of if it's kind of right. So yeah, it seems to be that it agrees with what we get in the previous kind of example when we use the CDF method. So now what's the evaluation of this stuff? Right, so well, kind of it's comparable difficulty, I would say, the comparable difficulty with cumulative distribution method. So, but in this case, the difficulty was into figuring out the range, and this is usually the difficulty in these cases. It was very easy to calculate the joint density of u and v. So, okay. All right. So this is this example. So now. Maybe kind of so we have not much time, but kind of maybe I'm not sure if I'll be able to do this example, the next example on this topic in 15 minutes that remain, but let us start kind of, and so and let's do even more complicated example. So example 3. Right? So now this example, well, it starts easy. So you have a x and y, standard independent oops, independent standard exponentials. And the question here is that joint density of U, which is equal just the sum of X and Y. Right? So, and V is equal to X plus Y. Right? So kind of, so one of them is a sum of two independent exponential. So he's exponential, sorry, not exponentials, maybe exponential random variables. And so sum of two independent exponential random variables, and another is just kind of X divided by X plus Y. Right, so X with respect to this two random variables. So, and kind of what's the joint density of this thing, and kind of what is the marginal densities, density of X plus Y. Right, and this is might be not kind of X plus Y, and so of U, marginal density of U and of V. Maybe not the best way to calculate the marginal density of the sum of two exponential random variables. We will see an easy example later. But kind of, so this is an example, right? So now how you can do it? So here you're given U and V. So what's about the inverse transformation? So X is equal to, you can see that X is equal to V multiplied, so X is equal to V multiplied by X plus Y. So it's equal to UV. Y is equal to, so now, if you know X already, kind of, then you can figure out that Y is equal to U minus X. So it's equal to U minus UV. So you can write it as equal U 1 minus V. Right? So this is the inverse transformation. So this is direct transformation. This is the inverse transformation. And so what about the Jacobian of this transformation? Jacobian of this transformation, of the inverse transformation. So it's absolute value of a determinant, and here will be the matrix, where you write that this is equal to d over u of uv, d over dv of uv. Here's d over du of u 1 minus v, and here's d over dv of so uv. Here's d over dv of u 1 minus v. Right. Okay, so So what is this? So it's equal to determinant, absolute value of a determinant, where he will have a matrix V, so the first derivative. Here's U, the second derivative. Here will have d over du, 1 minus V, and he will have a derivative of this thing, which is equal to minus u. It may be kind of, well, so kind of, what is it? So absolute value of minus uv minus cross product here minus u times 1 minus v. So it's equal, okay, so minus uv here, and here's minus u times minus v, it's cancel out. So we'll get that this is equal to absolute value of minus u, so it's equal to u. Okay, so this is the Jacobian of this thing. And after that, so after that we'll need to figure out what's okay. So what's the joint density of x and y, original kind of. So f of x and y. And so these are independent, two independent random variables, exponentially distributed random variables. So it's equal to e minus x. It's the density of one independent random variable multiplied by e minus y, the density of our independent random variable. And here's x and y, so they should be greater than 0, both of them, right? Or 0 otherwise. All right, so now, okay, so what about the joint, what about the joint density of u and v? So we plug in the formulas for x and y in this formula. So it's equal to e uv minus uv. So this is from this kind of thing, right? So multiply by e minus u 1 minus v. So calculating it, so minus uv, have minus uv, so it's e minus u. Okay, but also kind of, so here should be multiplied also by Jacobian, right? By Jacobian. So it should be multiplied by this Jacobian by u. And so we figure out what this is the joint density of u and v. So if u and v in a range of, so u small and v in the range of u large and v large, and 0 otherwise. And so now what's the range kind of u and v? So right, so now so this is kind of can be done formally, right, and can be done also kind of slightly informally, right? So maybe kind of for the formal derivation, you can look in the lecture notes. So informally, kind of you have a u which is equal to x plus y. So you're thinking about what's the possible range of u. Right? So the possible range of u is well, x positive, y positive. So u should be positive. Right? And you have v, which is equal to x divided by x plus y. And so you're thinking about kind of what's the range for v. So okay, so it's x divided by x plus y. So it should be between 0 and 1. right? So because x cannot be smaller than 0, and it cannot be larger than x plus y. So now, well, this is not trivial, but not quite kind of immediately easy to see, but kind of if you think about it, that the range of u and v, it just will equal that u is from 0 to infinity, and v can be anything between 0 and 1. So this will be the range of u and v. So okay, so now let's do it one of them, kind of one of these examples, kind of. So what's the density of u? Okay, so what's the density of the sum of these two random variables? So it's integral from f of uv dv. Okay, so now for a fixed u, it should be changing from 0 to 1. V is changing from 0 to 1, so integral here from 0 to 1. Okay, so it's equal to integral from e minus u multiplied by u over dv, where let me see if I'm doing everything right. Yeah, doing everything right. From 0 to 1. So it's equal to, okay, so E minus U. So this is the marginal density of U, and you can get the marginal density for V in the same thing by integrating from over this line. Okay, so this might be kind of overcomplicated example. And so, but so the point of this example, so in the previous example was not quite good, because you see that the Jacobian of the transformation in the previous example was equal to 1, so you didn't really need to multiply kind of by anything. So here's, well, there is a calculation of the Jacobian, so the point of this example, so you need to Jacobian to get the right density. Okay, the right joint density. So we have it here. Okay, so f of u of v. So this part was from just calculating the inverse transformation, but we also need to multiply by Jacobian, which is in this case was equal to u. All right, so that's it. So to summarize, summarize the PDF transformation method. PDF transformation method is very useful if you have a function, kind of a map of if it's a function of one random variable. In this case, it's kind of, well, very easy to do. So it's kind of, you should know how to do it. And when you get to the function of more than one random variable, to function of several random variables, then in this case, it's more or less easy to calculate the joint density, right? If you have a transformation from two random variables to two random variables, and it's one to one, then it's relatively easy to calculate what's the specific value density of a point, but it becomes more difficult to figure out what's the range. And it becomes not very easy to calculate if we have a function u is equal to f of xy, and this function is not one-to-one. Right? So it's a function, one function of many random variables. So example of these functions, right? So kind of, and this is important class of function. Example of this function would be like before. So if you have a u which is equal to x1 plus x2 plus so on plus xn, right? So if you have a function like that, so in this case, you can see that, all right, so this is a function of many random variables, which is not one-to-one. Right? So you have n random variables, and you take the sum of them, u is clearly not one-to-one. So in this case, the PDF method, right, PDF transformation method would say, find kind of v, kind of another random variable. So v1 is equal to something, v2 is equal to something, v n minus 1 is equal to something, right? To do this transformation, kind of using this pretty difficult. Well, you can do something like relatively simple. You can say this is kind of equal to x1, this is equal to x2, this is equal to xn, and so it's still possible to do. So the transformation is not very difficult, but still kind of looks not very easy thing to do. And so now the next time what we'll do, we'll see kind of maybe kind of it is possible to calculate the distribution of the sum of a random variable in an easy way, kind of, and this will be done by using the moment generating function. So, all right, so that's it for today. So kind of this was a hard